for this pandemic, and it is food. We have sufficient food. In fact, about 40% of the food that our country produces is wasted. Could our research efforts be helpful to those who are hungry? Also, as researchers, could we look into the indigenous medical practices, what our grandma has been practicing for infections, or the less known herbal, Siddha, homeopathic medical systems? These could be researched as an alternate medical system which could bring in health for the needy at affordable cost. We have everything in abundance. It is our duty to make it available, effective, and affordable. Just think of the death rate at present. It is 10 to 15% of the corona infected in the developed countries, but in India, it is less than 3% of the infected. People seems to be better prepared for this pandemic. In this context, the topic chosen for the webinar, namely materials for biomedical and energy, would be very relevant and useful. It's nice to have an international panel for sharing information and discussion. I thank the chemistry department at Loyola College, Chennai, especially Dr. Johnson, the head of the department, and Dr. Judith Vijaya, the organizer of this event. Wish you all to learn more and to do the needful for the needy in our society now and in the future. All the best for the webinar. Thank you.
Thank you, Father, for the felicitations. Leaders become great not because of their power, but because of their ability to empower others. Here comes our HOD, Head of the Department of Chemistry, Dr. M. George Johnson, to offer his felicitations and share about Loyola College, Department of Chemistry, and also about Reverend Father Lourdu M.Yeddanapalli SJ, a pioneer in the field of catalysis. Over to Johnson, sir.
Good afternoon, ladies and gentlemen. I am also happy to welcome you all for the international webinar, and I take this opportunity to thank Rev.Dr. Francis B. Xavier, SJ, Rector Loyola College, for the felicitations offered and for the excellent account on the contributions of Jesuits in science and research globally and in India. Thank you, Father. I assure you that we will follow the footsteps of Rev. Father Yeddanapalli. It gives me immense pleasure to share with you all the marvelous contributions of Rev. Father Lourdu M. Yeddanapalli to the Department of Chemistry, Loyola College, Chennai. Father Yeddanapalli joined the Department of Chemistry in the year 1946 and took charge as professor and head after obtaining his PhD degree from Princeton, USA and DSc from Lille, Belgium. He has graced the chair of the chemistry department for the past 25 years, from 1946 to 1970. During this period, he started several new courses in chemistry such as BSc Honors, MSc Physical Chemistry, MSc Chemistry and Research Program. He created his own chemical laboratory in Loyola. With one student, he began his research program in 1948 on the olefinic structure of the phenolic constituents of the liquid extracted from cashew nut cells. From a humble beginning, Father was able to expand and extend the scope of research. His intuition to research was really amazing, and he had a great foresight that resulted in guiding 25 students for PhD in various fields such as adsorption, catalysis, polymer, bromination, kinetics, chemisorption, cashew nut oil, terpenes, milk proteins, etc. Father was a devoted Jesuit, a fatherly priest, a friendly personality, a lovable character, and a silent guide and philosopher. He was the standing example of simplicity and devotion. His lecture was a revelation of the beauty of science and inspired the students to continue in science as his classes were incredibly productive. He insisted on having seminar every week for research scholars, and this unique practice continues even today for our UG and PG students in the Department of Chemistry. Father was one of the pioneers of chemical research in the immediate post-independent India and brought recognition to Lille as one of the centers of research. He was one of the outstanding chemists in India. He sowed the seeds of catalysis in India. In the year 1973, one of his students, Professor Kuriakose, who served as a professor at the IIT Madras, co-founded the Catalysis Society of India with Professor Bhattacharya of IIT Kharagpur. In the late 1960s, a few more students of Father, namely Dr. Paul Ratnasamy, Dr. A.V. Ramasamy, Dr. Sivashankar, joined the National Chemical Laboratory, where they made investigations in the manufacture of industrial catalysts of national and international relevance. His students reached the position of the President of the Catalysis Society of India. It is very fitting that one of the awards which this society makes biannually is in Father's memory. Several scientists in the catalysis community today are his students. There are a number of his students who occupy high offices in administrative as well as academic area all over the world, keeping Loyola flag and Father's name proud. The Department of Chemistry has produced so far about 120 PhDs, and I take this opportunity to thank all my dear colleagues for their devotion and dedication. We are happy to offer all our achievements as a rich tribute to these great scientists as we observe the Semi-centennial memorial of Father Lourdu M.Yeddanapalli. Thanks to Dr. Judith for the wonderful thought of arranging this international webinar in memory of Father Lourdu M.Yeddanapalli. Thank you and all the best.
Thank you, sir. As you correctly said, it is the right time to honor Rev.Dr. M.Yeddanapalli SJ for his wonderful contributions in science and research. Thank you, sir.
Thank you.
According to Mother Teresa, don't expect your friend to be a perfect person, but help your friend to become a perfect person. That is true friendship. A friend whom I have never seen or not talked with, but still able to publish 70 international Scopus Index journals with him is possible only because of Dr. Mohammed Bawadina, a professor from University of Bahrain. I request him to speak about the theme of the webinar and introduce the first speaker of today's session, Dr. Stefano from Italy. Over to Dr. Bawadina.
Okay, thank you for introducing me so much. So let me first thank the speaker for their registration. We have a good number and from different countries. So let me introduce now our first guest speaker, which is who is Professor Stefano Bellucci from the National Institute of Nuclear Physics from Italy, Friscati, I guess. So let me introduce him a little bit. He has a PhD in elementary particle physics at CISA in Trieste. He has published more than 500 papers with high citations. His research interest includes, but not limited to, of course, theoretical physics, condensed matter, biophysics, and nanotechnology. He has supervised over than 40 PhD and master students, and he is also a reputed scientist and he is editor in international journals. So, Stefano, the talk is yours, so you can start your presentation. Thank you.
Thank you very much. So let me put on my slides.
So it's interesting, Stefano moved from particle physics to nanotechnology.
Yeah, that happened long time ago. So I hope you all see my screen. Today, I would like to speak about the use of advanced materials based on nanoscience. They have almost ubiquitous and enabling applications. But today I will concentrate on the applications in the biomedical area, as well as on the precautions that must be taken when handling such materials. And I'm honored to be here, and I would like to thank the organizers and thank in particular Professor Budina for the kind introduction. So here is the place where I work, the National Institute of Nuclear Physics, and here I have 3 laboratories under my responsibility. So what is the activity that my group is carrying out over the past 23 years? We synthesize different types of nanomaterials. We use different types of microscopic and spectroscopic characterizations to check what we have obtained. Moreover, we functionalize chemically, but also with physical methods, the nanostructures that we prepare, and then we concentrate on the applications that go from sensors to drug delivery, to electronics, to composite materials for aerospace, to different type of applications also in the area of energy. We are sustained and helped in our group by several collaborations, including collaborations on transport, electronic transport, modeling and simulation, also structural properties that are needed when we design our devices. So let me first introduce the nanoparticles and the uses that can be done with them. You can see that these nanostructures have practically an infinite amount of potential uses. I have tried to group them here in areas, for instance, biomedical, healthcare, food and agriculture, industry like industrial additives, electronics, environmental applications for remediation, for instance, with respect to heavy metals or organic substances in water, and renewable energy, and also textiles. Now, I've divided here into 4 sectors, the main areas of progress recently in the past, let's say, 20 years of nanotechnology. First of all, how can we define nanotechnology from a methodological point of view? We can define it in many ways, but one way that I like is define it as a science of manipulating matter at the molecular and at the atomic level to obtain materials with enhanced properties from the chemical-physical point of view. And these properties must be enhanced just because of the presence of this nano size dimension. Here I have IT, information technology, energy, consumer goods, and medicine. Well, as I said, the scale of lengths approximately ranging between 1 and 100 nanometers must be responsible for the fundamental innovative properties and functions. Otherwise, we don't talk about nanotechnology, we just talk about nano objects. What is the miracle coming from nanoscience? What is the reason for it? It's essentially one very simple fact, and is connected to the large ratio of surface divided by volume of these objects. This yields a very large surface area for nanoparticles. To fix ideas, imagine that the number of surface atoms in a particle of 300 nanometers diameter is only 5%. Whereas if you scale down by factor 10 to a nanoparticle of a diameter 30 nanometers, then you get half of the atoms concentrated on the surface. And here's a famous slide taken from internet, the CDC, a center in Washington, D.C., where you see what happens when you scale down from a block of gold, where the surface is only 6 square meters. If you want, it's a room of 8 feet by 8 feet. And then you scale it down to the nanometer. If you divide it into blocks, 1 nanometer each, then you get a surface which can cover easily a state like Delaware, for instance, 2,500 square miles. Okay, here is the nanometer scale. You can see that we range from atomic scale, which is 1 angstrom, so 1/10 of a nanometer, all the way up to small molecules, to fluorescent proteins, and we are already talking about 10 nanometers, Here is the range where you see quantum dots and nanocrystals, to colloidal particles, for instance, gold nanoparticles, about 100 nanometers, and then to life. You see the bacteria, typical size is micron. The cell, the animal cells, typical size is several tens of micron. Our interest these days is catalyzed by viruses, and viruses can range from 200 nanometers up to several microns. So the dimension can go from the size of a man, then you reduce by factor 1,000 to 2 millimeters, you get to the size, for instance, of a mosquito. And if you scale it down by factor 1,000, you get to typical size of eye of an insect. And down you get to the nanometer, which is the base, the size of the basis of life. This is a schematics for DNA, which is 2 nanometers wide. We have simply divided by 1 billion the scale of a human being to get to nano-sized objects. Here in nanotechnology, there are 2 types of methodological approaches, top-down and bottom-up. Top-down, you simply break down things, and bottom-up, you combine things up like you do with these Lego bricks. The bottom-up approach has been exemplified and used because of its scalability at the industrial level. Here you see 2 books that I've edited on the topic. Essentially, this nanotechnology is also curious. It existed since a long time. In the late Roman Empire, in the 4th century after Christ of the current era, there was a famous artist called who created this cup. It's survived until nowadays. It's preserved at the British Museum in London. And depending on the source of light, it shows different coloring because it's observed in reflection or in transmission. And the different optical properties are due to the presence of noble metals nanoparticles like gold and silver. And the size of this gold and silver is about 50 nanometers. Another example is provided by medieval churches where metallic nanoparticles were included in the windows, in the glass-stained windows. And you can see the method of preparation of nanoparticles in this case was typically top-down. They were crushing metals, powders, until they got into the nano size. We need to characterize these nanoparticles, and nowadays we are able to do that by different methods. Here you see an example of use of an STM, a scanning tunneling microscope, that was realized in 1990 at IBM. There's even a curious fact, 2013, the smallest film in the world was realized using atoms and allowing them to self-assemble on a surface of silicon. And that shows like a cartoon where a boy made of atoms is playing with a ball. Carbon is the basis of life, and carbon family is quite interesting family because it includes, in addition to graphite, which is made of several layers of what nowadays is called graphene, bound together very weakly by a pi-pi orbital type of bond. It's also containing, of course, in the family, cubic lattices like the diamond with its beautiful optical properties. And fullerene that was discovered in the 80s, made of not only hexagons, but also pentagons. So you need defects to close a graphene sheet into a spherical shape. But you don't need defects if you want to close it into a cylindrical shape, as it is done in a carbon nanotube that was discovered about 10 years after fullerene. And graphene was isolated even 10 years later. So let's start with the carbon nanotubes. As I said, they were discovered in the 1990s in Japan. They're hollow cylinders, long and thin. You can have 2 types, 1 layer, so-called single wall nanotubes, a multi-layer or multi-wall nanotubes. They have a tremendous aspect ratio. That means the ratio of the length of the tube divided its diameter. They're practically quasi-unidimensional objects. The aspect ratio can get to the level of 10 to the 7 very easily. What's so special in a carbon nanotube? First of all, as I said, it's high aspect ratio, which makes it a one-dimensional structure, but also its elastic modulus. Its Young modulus can beat any special steel that is in use very easily above 1 terapascal. Also, the ability to carry high density of currents can outdo the current density transported by copper, and it can reach 10 to the 9 ampere per square centimeters. Moreover, from the thermal point of view, it has a very high conductivity at different temperatures, from room temperature up to very, very high temperatures. And these values are exemplified here, several thousand watts per meter per Kelvin. So great properties, but how do we make them? We can make them by 3 methods: artist charge, laser ablation, or those are physical methods, or a chemical method, that is the deposition of chemical vapors. They have advantages and disadvantages. Typically, the chemical vapor deposition, which is the one that is used industrially, is essentially has the drawback of producing nanotubes only when catalyst metals are included in the reaction, and so a lot of impurities are present in the final product and need to be removed. So here you see an example of our early production by physical method of very, very pure carbon nanotubes. Here I show you also different magnification, and you can see that these nanotubes are mechanically very strong. This is a multi-wall nanotube, 20 nanometers in diameter, and it's obtained by artist charge. But what are the applications? One can think that they're futuristic, but no, they're already in the past. For instance, well, I'm like all Italians, I like very much the car racing. In Formula One, our national manufacturer, the Ferrari, already used nanotechnology 13 years ago, and the Ferrari 2007 with the driver Kimi Raikkonen was winning of a year one championship. It contained carbon nanotubes in several of its components. Nowadays, applications oriented towards the environment are very popular. And here you see an example, 2016 at the Salon for Automotive, the presentation of this Symbiosis car. It's a Symbiosis vehicle running on solar piezoelectric energy. And here carbon nanotubes are used because of friction. They are scattered all over the body of the car. By the way, this car is a concept developed by students, students in a college in California and students in Germany. Together they join forces. On the right-hand side, you see flexible screens that nowadays are already being proposed by Samsung, for instance. Here the display is known as OLED, organic light emitting diode, and the advantage is clear with respect to LCD screen technology because you don't need a backlight. The security to control the pixels is used in the glass. Nanotechnology can be used also in restoration, and here you see calcium hydroxide nanodispersions that are typically used for nanocleaning. I put on the left-hand side 2 images of a fresco in Florence by the Beato Angelico, and on the right-hand side, the particles that are used for nanocleaning. I'll also like to mention commercial products for cleaning. On the right-hand side, please look at treated surfaces, for instance, of big handles, door handles in commercial centers. Treated surface shows a perfect clean aspect, whereas untreated surface gets polluted, dirty, contaminated nowadays, even with viruses. And you can see also tools for work, treated and untreated. On the left-hand side, you also see another interesting feature that is called biomimetic, because it just imitates nature. It is the so-called lotus effect. The lotus leaf doesn't let water absorb on it, And here there's a cotton layer that has been coated with a nano coating. This nano coating based on titanium dioxide, and it doesn't allow any droplet of liquid to stain or to wet the surface. So you have different applications in textiles. Also from the energy generation, here you see a curious gadget that is called Power Felt that can produce 100 millivolt per square meter due to the presence of a gradient of temperature of the body of the runner with the external environment. So if you assume about 17 Celsius of difference of gradient in temperature, that's the amount of potential difference of voltage that you can create. Finally, in cosmetics, nanoparticles are being used currently, for instance, for sunscreens. So basically, I hope I convince you in this brief introduction that nanotechnology is pervasive and is also enabling. It allows to bring mankind onto a technological level that was inconceivable before it, pretty much like it happened in the end of the 19th century with the discovery of electricity that was pursued for replacing gas, the lightning of cities, and then it ended up giving us the possibility of realizing computers, portable phones, and all sort of things. So basically, because so many uses are already in place and many more are coming in the near future, we need to worry about the impact on the environment and on the human health of these nanoparticles, in particularly on professionally exposed workers. So that's my next chapter, the impact of nano on health and environment. So the impact has been treated in different books that I've edited or co-authored. Here on the left, you see the uses in biological applications for Springer, Verlag, editor. On the right-hand side, this is an important book that we produced in 2010 to assess the potential damages and the best practices to avoid them produced by exposure, unintentional or intentional, to engineered nanomaterials, and especially the effect on occupational, on workers, essentially. So we produced it and was published in Italy, but it was then assumed and pursued by the European Union, that then used our recommendations for a directive, a European directive in 2015, disciplining the uses of nano objects in any commercial application in Europe. Okay, so the grand challenge of nanotechnology includes also the fact that the property of nanotechnology do depend not only on the diameter, but also on the shape, but especially what surrounds the particle. That can sound strange or weird, but in fact, it is very important when this property, very important when you consider biomedical applications like we will do today. In particular, I want to exemplify the notion of a biocorona. What is a biocorona? On the left-hand side, you see a nanoparticle at synthesis in the lab as we created. Then let's suppose that the nanoparticle crosses the biological barrier. It's inhaled or injected into a living organism. Immediately, the living organism will surround the nanoparticle with biological material, and that will cause the realization of a biocorona surrounding the nanoparticle. Suppose now the nanoparticle, surrounded by its corona, will get near a cell. Normally, what happens is the cell in front of nano objects opens up, and that's the endocytosis mechanism by which nanoparticle is included in the cytoplasm of the cell. When it is in the cytoplasm of the cell, the color of the biocorona is changed. What do I mean by this symbol? I simply mean that the material now around the nanoparticle will be changed, and you get a new biocorona, and you see here a lysosome with a vacuola where the nanoparticle is put for some time. Maybe at that point it will release some drug, or it will be used for imaging through some diagnostic mean. In the end, there will be the exocytosis, and the nanoparticle will leave the cell and eventually the living organism. So basically we have a scheme here that lists epidemiological and toxicological considerations. From the epidemiological point of view, you see nanoparticles produced, for instance, during combustion processes. These are very, very common, produced unintentionally. And now here you see on the bottom, you see the nanoparticles produced intentionally because we want to use them in industrial applications. That's the notion of nanotechnology. Nanotechnology, of course, attracts a lot of attention because of its powerful applications, but we need to norm and regulate these applications, eventually taking into account toxicological effects and industrial hygiene best practices. So here you see some examples of toxicity assessment we did 12 years ago, cell proliferations, just for illustrative purposes. And here you see our work, 2014 and 2011, where we use multi-wall carbon nanotube to create a film. And this film was used for treatment of cancer cell of the skin. So basically, this introduces already the notion that we can use nanotechnology to carry out medical applications. What is a nanomedicine? Nanomedicine we can define as the preservation and improvement of the human health, making use of molecular tools and molecular knowledge of our human body. Now, nanomedicine from this point of view is an equally important area of application like engineered nanoparticles, like those that we already saw and others. For instance, on the right-hand side, you see treated surfaces and untreated surfaces react completely different to rain. So you could avoid using windshield wipers in the cars. You can have no need to clean your display because fingerprints will not be able to stay onto treated surfaces. On the left-hand side, you see nanomedicine, conceived, illustrated as the medicine of the single cell. And here you see the many facets of a nanomaterial, for instance, a nanotube. A physicist or a chemist see this nanotube or this nanomaterial as some specific object that can be characterized physically and chemically. But the pharmacologist will be interested into modifying this object by, for instance, drugs, pharmaceutical compounds. A biologist will study them in interaction with living organisms, and a physician will see them with the eye of either diagnostic or therapy or theranostic, combination of the two. So basically, because the nanomaterials are made by several parts, either organic or inorganic, the possibilities become practically infinite. And here you see a scheme of what is the platform and nanoparticles that can carry many, many functions, from different drugs to contrast enhancers to improve its use in diagnostics, to targeting moieties that help to deliver the particle and its cargo precisely to a specific tissue or organ, to an enhancer that will allow the nanoparticles stay a long time in the body without being expelled. So here you see examples of, we did this about 16 years ago. We prepare short nanotubes, and we were able to practically engineer the length of these nanotubes by our recipe, and then use the carboxylic group, COOH, that we created onto the nanotube by functionalization in order to grow silica nanoparticles onto the different spots. The applications are, for instance, in magnetic resonance or in imaging for diagnostics. And here you see real pictures at the transmission electron microscope of the samples that we realize. As you can notice, you can have many different configurations of the nanoparticle of silica that then can be stained, can be colored, can be magnetized, can be a platform, and the nanotube. Of course, the cytotoxicity was assessed. This also was done 17 years ago by us in this important work. We carried out tests on Jurkat T cells, part of our immunitary system, and studied the conditions under which these nanotubes can induce apoptosis or can reduce the proliferation, and also can induce reactive behavior in cells like oxidative stress. We talk about the possible bad effects. Now let's talk about the potentially terrific effects that in positive we can have from nanoparticles on the health and also on the environment. A well-known example is the use of biocement for bone applications for fixing microfractures. For dental applications, here you see even commercial products are using, like toothpaste, using nanoparticles to fill small microcavities in the teeth. Another interesting area of application is the cancer therapy, where nanodrugs can be delivered in a targeted way. Here is a review paper we wrote about 6 years ago on the state of art at that time. Nanotechnology have been used since a long time for curing tumor. An old way of curing tumor is the hyperthermia. Basically, you up the tumor until the cells go into apoptosis, let's say at 45, 46 Celsius. But nanoparticles of iron oxide magnetized have been used in Germany at the Berlin hospital La Charité for curing prostate cancer, using the fact that nanoscience here gives you the specificity. So instead of heating up the whole tissue, tumor cells and healthy cells, thanks to the little tiny nanoparticles of iron oxide paramagnetic behavior, they can be put in an oscillating magnetic field, and only the tumoral cells, who are typically greedy and they eat up, so to speak, those nanoparticles because they are sugar-coated, only those malignant cells are being destroyed. And here you see examples on rat, and basically you see from the thermotherapy, the red spot is where in the eye orbita of the rat, where the tumor is being cured. So we have a tool for diagnostics, as I will show you in a minute, for imaging techniques and also for therapy. Combining them together, these magnetic nanoparticles can produce theranostics effects. And here you can observe and monitor the tumor, for instance, in this rat, which is put into a magnetic induction coil, and at the same time, the administration of these magnetosomes particles can cure the tumor, and you can observe the regression of tumor in real time. After 30 days, the disappearance of tumor is documented. That's the notion of theranostics. Magnetic nanoparticles, it's an example. We use a photosynthesizer, can deplete the tumor and at the same time observe this depletion. I promised to talk about diagnostics. Nowadays, the scientific world is engaged into reducing a lab on the size of a chip. So all the analysis that can be done, for instance, to detect SARS-CoV-2 using PCR or ELISA tests, nowadays we are struggling to propose small chips that will be endowed with the capability, with the functionality, thanks to nanoparticles, to detect this virus on the size of a fingertip. And here you see an example of a chip that carries on the functionalities of a whole lab. The advantage is not only miniaturization, but it's fast analysis. It doesn't take any longer half a day. It can take 20 minutes. The other advantage is, of course, that it's portable. You don't need to carry the sample to the lab. You can carry the lab onto the place where the sample has to be collected. So instant analysis. and portability. Sensors can be based on spectroscopy, as it is the case here. Basically, you need to have, in order to observe the signal, because these signals by a few molecules are typically very tiny, you need an amplifier. And the amplifier is provided by the nanoparticle substrate on which the molecules you want to observe are deposited. And here is a new science that is being developed. It's called surface-enhanced spectroscopy. In particular, this is Raman spectroscopy, it's a vibrational spectroscopy, and it has been used, for instance, in vivo on rats. Applications of biosensors go very far. They can go to, for instance, security, anti-terrorism, and you can combine biosensors to detect different types of toxins, pollutants, poisons, viruses that can be intentionally delivered on an area, and have a collective data sampling and fast data analysis that will allow you to immediately intervene, step in the area that you are surveying, and remedy. So here you see the elements of a biosensor based, for instance, on DNA on a chip. You start from the samples that can be very varied: cell cultures, human samples, blood, urine, saliva, food samples, environmental samples like air, water, soil, or vegetation. Then you need a transducer that can be a nanoparticle, a nanowire, a nanotube, a FET device. And then on the right side, you see the acquisition system. And I should have put also another aspect, that is the treatment of the data by algorithms like artificial intelligence and machine learning. Here you see an example of what we did in 2014 with a project financed by the NATO organization, the Transatlantic Alliance, USA, Europe, where electrochemical sensors were developed in my lab using composite coatings based on carbon nanostructures. We compared the effectiveness of nanotubes with graphene and with nanotubes functionalized by aminic groups. And we concluded that good sensors on screen-printed electrodes are provided only by nanotubes with aminic functionalization, but not by pristine nanotubes, as well as by graphene. More recently, NATO has financed another project at Direct. This is the project on photonic crystal sensors, sensing biological and chemical agents to very, very small scale. We're talking about 100 femtograms. That means down to few molecules of different analytes that can be of interest, like biological toxin, chemical toxin. And here you see the principle is a grating realized by holographic laser techniques, and the different colors are due to the different particles, nanoparticles, that are dispersed and form a grating, a lattice onto the in the inner part of polymers. More recently, about a month ago, I coordinated a new proposal for the Horizon 2020, the European Union program that is closing this year, and the title is Novel Smart Sensor for the Early Detection of Concentrated Viruses in Air Filters. Basically, this project proposes the realization of a novel sensor for measuring respiratory virus, like coronavirus, from in aerosol in confined environments, suppose, for instance, a hospital. And the idea is very new because it couples the advancement in airborne pathogen point-of-care diagnostics with the field detection based on a printed sensor, electrochemical sensor, pretty much like the one I showed you 2 slides ago, together with the enhanced selective sampling that is provided by what? By the use of new 2-dimensional nanomaterials like graphene, but not only graphene, transition metal dechalcogenides like molybdenum disulfide or hexagonal boron nitride. All of these allow us to create functionalized membrane by putting a selective bioreagent that is able to react to the targeted pathogen onto the 2-dimensional material. So this way we have a new electrochemical sensor for viruses. The idea is also to use a paradigm of IoT, Internet of Things, collecting the data and analyzing them by distributed system, so that the signal processing can be then implemented by, for instance, machine learning engines. And here you see the schematics where different masks or different filters, this can be used for personal protection equipment as well as for air filters, can be then handled by a centralized program that can then putting in comparison different historical series of viral charge detection, as well as different places in the hospital, for instance, where the masks are worn by different type of individuals, and at the same time be able to analyze very fast and elaborate very fast the information we get. So at this point, the last topic I'd like to treat is the drug delivery by using nanotechnology. What is the principle I like to convey to you? Normally, we need to take a pill, an aspirin or anything, several times during the week, maybe once a day or even 2 times a day, because the dose of the drug is high enough, even too high, for a few hours, but then it goes down. Instead, by using drug delivery systems, we can have an average desired level of efficacy for a prolonged time. And here you see different example of drug carriers. Here I show you what we did recently to bypass the brain barrier. There is a barrier between the brain and the blood that doesn't allow pharmaceuticals to reach easily the brain. So we think of passing through the nose for a selected delivery. And basically our idea is to allow the drug to cross the membrane and reach the brain, avoiding in this way collateral effects or avoiding invasive care like lumbar ejection or surgical operation. So here is our alternative. Use the axonal transport between support cells in order to exploit the axonic termination of the olfactory bulb. And it's also very appealing, the fact that we can use aerosol, like a standard home device, home equipment, to self-curing, self-therapy. So basically here, there are several steps. On step 1, you see the absorption by dendrites. Then on step 2, you see, so this on the right-hand side, the molecules are coming to the dendrites. And then the axon allows the drug to pass until it streams into the brain. This is called axonally mediated transport. Clearly, we have several problems. First problem we have to solve is the fact that there is something called mucociliary clearance. Quickly, all molecules in the nose are eliminated by the movement of cilia that move in a synchronous way and eliminate the drug and push the drug towards the rhinopharynx. To avoid this, we used mucoadhesive nanovectors, in particular alginate, here to increase the retention time in the nasal cavity. And here you see the nanoparticles of alginate loaded with drugs. Another application we already finished about 3 years ago. It was a long project where we cured, by the same principle, delivery of pharmaceutical drug, in this case microRNA, a nucleic acid, using as a carrier, in this case, shortened carbon nanotubes, and the targeted disease was a pediatric disease, children disease, the so-called pulmonary hypertension. It was a research where we essentially delivered the microRNA into endothelial cells. You can see here fluorescence images documenting the absorption by the cells. And here is the transmission electron microscope images showing the short nanotubes. Here we talk about nanotubes 500 nanometers long, very, very short, and then much more biocompatible than long nanotubes, into the cytoplasm, where they release the drug. And in vivo, we documented by sponge implantation the reduction of symptoms. This drug allows the proliferation, unwanted proliferation of blood vessels that causes the death of the small patients, of the children affected by this disease. We reduce by 50% the length of the vessels and the number of vessels per node into the pulmonary epithelial tissues. That shows good prospective applications for therapeutic angiogenesis and vascular remodeling. Because of short of time, I'm not going to talk about graphene and its manifold uses. This is the novel material of the past few years. I've been for like 4 years the spokesperson of my institute for the graphene flagship, a huge project about 1 billion euro dealing with graphene. But I have no time, and I thank you for your attention.
Hello, thank you.
Yes.
So I have a few questions. Thank you for this insightful presentation, and the audience are reacting very good conditions. So I have a few questions, but I try to resume between them. So let me ask the first, which is related to our situation now. Can multifunctional nanoparticles be helpful in treating dreadful disease? I think they are talking about coronavirus, and how nanomedicine can be used in this case.
Yeah, as I said, our project NoseCov is aimed at detecting at an early time, very fast, the presence of the virus. Another possibility is to deliver pharmaceuticals that are being now experimented. People talk about before about chlorhexidine or hydrochlorhexidine and other drugs like the tocilizumab, which people now are experimenting drugs that were used for other disease, that were conceived for other disease like Ebola, for instance, this, or for joints diseases like arthritic diseases. Tocilizumab is precisely that. They're trying to use it with some success. My idea is that nanoparticles can be used as carriers to allow these drugs to be internalized by cells much more easily, and thus prevent the virus from using its spike protein to hook up the cells and then start proliferating. So we have three mechanisms: drug delivery to cure the symptoms, drug delivery to avoid that the virus can attach to the pulmonary epithelial cells, and early detection of the viral charge through masks connected with not simply masks to filter, but also masks that will measure in real time the viral charge, the viral load in distributed systems. So being able to connect data in space and time in a matter of few minutes, allowing immediately to interrupt. You see the new situations in China, the new situations in Germany and everywhere else. It's important to step in immediately, timely, to stop the people who have been touched and avoid proliferation. Other possible applications of nanostructures have also to do with devices, electronic devices that would allow implementing a better treatment of data, localization of patients. But I think the main will be they will be detecting and therapeutic applications.
Yes, I think that's why some of them, they are asking about biochips and some biosensors in that field. So let me ask about the other part, what you were talking about. It's about biocement. Someone is asking about, can you give an example about biocement in dental application?
Yeah, sure. Nowadays, apatite and hydroxyapatite is being used as a matrix for reconstruction of artificial bone. This can be used for this hepatite and hydroxyapatite need to be reinforced because their mechanical properties are not so good. So from this point of view, nanoparticles of titanium or other mechanically resistant and biocompatible materials can give, in the end, a composite material made of a matrix of apatite or hydroxyapatite and with a filler, which is made of nanoparticles. And in the end, this can be used for prosthetics, even for bones, reconstruction, and for artificial bone. Like, one of the main problems with dental implants nowadays is the fact that the teeth must be very, very short, the artificial teeth. Otherwise, during the biting, they can break at the root. They can break where the implant has been placed, because what breaks is not the implant, it's the bone in which the implant has been put. Normally, these patients, they have very thin bones that have been deteriorated by age, by inflammatory processes, and so on. So what is important is to reinforce these bones. And what this is done regularly. It is not entirely new. By now, it's already, I would say, half a decade that this is being used successfully by dentists. And basically, the idea is to use a composite material to stimulate the reconstruction. You have a twofold effect. After the implant of this material, this nanocomposite, the body produces new tissue. It's stimulated by this presence to surround the seed, the so-called seed, with new tissue. On the other hand, the seed itself provides the new tissue with sufficient texture and sufficiently high mechanical properties. Then the implant can be made by the standard techniques.
Okay, there are some other example about, let me choose, something related to nanoparticles of titanium oxide. Titania, so how to enhance the physico-chemical properties by doping or something like that?
Well, I mean, titania is being...
as photocatalyst,
titania
for photocatalyst.
That's certainly a very good suggestion, but let me bring about another famous application that was realized in the middle 1990s. So we're talking about really a long time ago, 25 years ago, only 2 years after in the United States, President Obama launched the National Nanotechnology Initiative. This initiative yielded its many fruits and its many results. The first one of which, however, was an achievement by a private company, which is called DuPont. This DuPont is a multinational producing many things, including paint. And actually, the highest return of investments in any nanotechnological product so far is still this old discovery of 1994, 1996. That was the paint based on TiO2 nanoparticles. So you mix TiO2 nanoparticles, titanium nanoparticles into the paint, white paint, and the result is very bright from the light point of view, very economical because you need only a thin layer of paint to give the total coverage of the wall, and at the same time, very easy to put in place because with the brush or with any tool, these titanium particles, due to their friction, to their tribological properties, they allow the paint to be homogeneously distributed. That was the topmost application. I cannot hear anymore. Hello?
We cannot hear Stefano, I think.
You cannot hear me?
No,
Can
it's
you
okay.
hear me?
It's coming back. Okay, no, it's coming back.
So I don't know if, so basically I was bringing about the example of this paint based on titanium nanoparticles that allow better performance. This is the highest value from commercial point of view, that has been obtained so far from titania. Titania is used for sunscreens, as I told you, and is used also for catalytic properties, like you're saying. And people are trying to use it also for some aspects of solar cells.
Okay, let me ask another question. Something I don't, this isn't linked. What is the relationship between IoT and nanotechnology? Do you have an idea?
Yes, sure. I mean, IoT basically is is a way to handle a lot of informations and to connect different aspects of our life in real time and handling the complexity related to it. It has applications for domotics, it has applications in defense, in aerospace, in biomedical. So basically the IoT then is an approach. Using Internet of Things means that we will have different things, and these things will be digitalized and put in connection to each other. From this point of view, I also would like to bring about another famous word that is actually two words, that is digital twins. That's another type of approach that will allow to schematize any process, even complicated, by its digital equivalent, solve the problem in the digital twin, and then bring the conclusions to the real system. Now, IoT then needs, in order to be interesting, needs, for instance, sensors. Need actuators, need robots. All these type of devices are guaranteed to be improved in their performance by the use of nanoscale materials, simply because of what I said before, that the surface of a nanoscale material is a very active surface, and you need to use nanoscale materials also if you want to reduce the cost, if you want to reduce the weight. Imagine applications where you are bringing a payload into 400 kilometers height. You need to lower the cost of launch by reducing the size, the weight. So basically the Internet of Things is a method, is an approach, but without sensors, without transducers, without actuators, you cannot make any efficient use of this for our society. And nanotechnology is vital in order to have state-of-art or beyond state-of-art sensors, beyond state-of-art applications and devices like actuators and transducers.
Okay, there is some question.
I cannot hear.
Okay, just one last question. We close because Professor Rabah is waiting, and we need to move to the next session. Only, is there any relationship between the synthesis, like normal chemical routes, and biosynthesis on the properties, for example, in terms of biomedical application like hydroxyapatite or titanium particles, titanium dioxide particles, etc.? This is the last question. I think we can close.
It's a very interesting question, and as you know very well, in the past several years, people have tried to use the biological organisms like plants, for instance, to produce nanoparticles. Clearly, there are challenges to be resolved. From this point of view, the use of green methods to produce nanoparticles and in general of green chemistry is very appealing. One example, I now finished one investigation with a group of chemists of agriculture, of food, and what they are doing, they're using, together with us, we are using waste of beer producing companies, some waste of plants, of cereals, etc., for realizing nutritional and pharmaceutical principles by using extractors, eutectic extractors of natural origins, what is called NADES. Another example, we are now proposing another European project that was very recent, 15 days ago. I'm directing another proposal where we use filters to remove virus from waters. I didn't include this because of lack of time. It's a project which basically uses filters and ozone. Ozone to disinfect. Ozone obtained from air by a device, portable device. And then this ozone leaves residuals, like, for instance, fragments of the virus, that need to be removed. We remove them by carbon absorbers, but these carbon absorbers we do not fabricate by these methods I illustrated, chemical vapor deposition or some other. We make by thermal method using waste of fruits and waste of vegetables. For instance, the bones of nectarines or the skin of different seeds like nuts or almonds. And there is a patented method we developed in conjunction with a Georgian group so that we can use waste coming from natural environment in order to produce these carbon filters. So I now say goodbye. And,
okay, thank you.
Thank you very much.
We thank you so much, Stefano, and hope we will have another opportunity to make another webinar or conference. And now we move to the second speaker, and introduce.
Thank you, Dr. Stefano and Dr. Baudina, for a very useful and wonderful session. There were many questions in the you participants link, and I have given your email ID so that they can ask you the questions. Thank you. Next, we move on to the second session. Now I request Dr. Rabah to deliver his lecture on Advanced Plasmonic Materials for Biomedical and Energy Applications. To say very few words about him, he is a CNRS Research Director and Group Leader, Institute of Electronics, Microelectronics and Nanotechnology from University of Lille, France. He received his PhD in chemistry from the University Paul Sabatier in France. He is an associate editor for ACS Applied Materials and Interfaces and also a guest professor, China University of Petroleum, China. His research interests are in the area of functional materials, surface chemistry, and photophysics of semiconductor metal nanostructures with emphasis on biosensors, photocatalysis, and nanomedicine. He is the author of 580 plus research publications and wrote 38 book chapters in various subjects related to nanotechnology, materials chemistry, and biosensors. He has 12 patents to his credit and his H index is 68. Now, over to Dr. Rabah.
Okay, good morning. Thank you. Just try to share my screen. Okay. No, we cannot see my screen, I guess.
It's coming, just...
Okay, it takes time? Okay.
It takes time, maybe.
Alt?
Alt tab. Yes, it's coming now.
Well, I will wait for probably a few seconds, then if it's not, otherwise I'll do the... Sorry?
Yeah, we made the test last time.
Just a second. So I don't need this. Otherwise, no. Sometimes I have to get out probably and get in again. Okay, let me just try again. Okay. Okay, it should be okay. You can see it? No.
Not yet? Not yet?
Not yet. Why not yet? Okay. Is it better now?
It's coming now, yeah. Make it full screen, Rabah.
I did. On my computer, it's a full screen. You don't see it in a full screen?
No.
Alt tab. Okay, let me do this. It's the same. You don't see it in a full screen.
This is showing the slides, all of them.
All of them? Because I think it takes time. It's quite slow. That's the reason, because I'm on a full screen and I was on all slides before. You don't see it still?
It was before, but now it's getting to the...
Okay, let me do it differently.
Now it's coming like one slide, but it's not full screen, as you said.
Well, yeah, I don't know what to... It's fine?
It's okay, we can go like this.
Okay, I'm really sorry for that. Good morning, everyone. First, I would like to thank the organizers, Mohammed and Judith, for this kind invitation. I slightly changed not the topic, but the title, because I think when I started working on both energy and biomedical application, it became just too long, and for 40 minutes, it's just impossible to cover everything. So I just reduced or focused more the presentation on biosensing and biomedical application. But as you have seen from the previous nice talk from Professor Stefano Bellucci, I will mostly focus on graphene. This is very nice because I think he addressed some of the results on carbon nanotubes, but as you know, certainly there are a lot of things that graphene and carbon nanotubes actually have in common and share as well in terms of surface properties, functionalization schemes, and also applications, because mostly what people did indeed is just taking whatever they have learned from carbon nanotubes and then try actually to apply the same concepts and schemes to graphene. So I put this very beautiful images actually I have taken at the end of February in India. So I think that was the last traveling for me outside. So I came back on the 28th, just 2 weeks after we were locked down for a while. So I think life indeed is just not the same as it was previously, but hopefully soon we all get together and find a better way indeed, and the life just becomes normal as it was. So I'm coming from an Institute of Electronics, Microelectronics and Nanotechnology. This is a CNRS, so it's a real research institute, which is situated in the north of France on the campus of University of Lille. It's a platform, it's a technological platform, so it means people mostly make devices and, of course, apply devices and characterize devices. The Institute is there are 5 platforms in France, which are recognized as platforms that are quite big, so you can see, the circles are in the north, east, west, southeast, southwest, so our platform is one of the biggest in Europe, and with about 500 people working, including permanent staff, engineers, technicians, PhD students, and visitors. And there are about 25 research groups on different topics, and mostly different axes about materials, nanostructures, physics, micro nanosystems, optics, telecommunication, a lot about acoustics and instrumentation. We joined the Institute about 5 years ago. We still physically were not inside, but we're another building which is about probably 400-500 meters away. So this is my group. So we're 8 permanent staff, and we're about 30 people, including PhD students. Yeah. What? Whoa. And now? Okay, it means because it's on the slideshow, it's full screen on my. So okay, then I continue like this. It's much easier. Okay. you didn't miss much. There's no science until now, so just mostly the presentation of the Institute and the group. So you can see it's quite an international group. So we have about 20 nationalities from different countries, and even from Africa, from Middle East, from Europe, mostly, and Asia. Our activities are centered about nanoparticles, nanomaterials, in different, I would say, large sense, because we make different types in thin films, but also in rods or wires or particles. And we have a specific expertise as well on the surface modification and functionalization to acquire, just to actually make or add functionalities to these nanostructures. Otherwise, we call smart versus just passive. So we make them more smarter than they were before. So adding through adding functionalities through surface modification. And you can see, indeed, what we're interested in is there are different types. I separated the bio and the energy type or sensing type, environmental type activities. So on the top, indeed, we develop a lot of nano systems for drug delivery, but also as antiviral or antimicrobial systems. But also, we're concerned with looking at how these nano systems impact the living species, such as copepods or in water, and see indeed whether we can somehow use these nanoparticles to bring a positive effect, not just a negative effect. I think a negative effect, of course, all of you know about the toxicity of these nanostructures, and particularly when they get in contact with other pollutants within the medium. So that's one aspect. The other aspect is indeed how we can also, the opposite, clean up this or treat these species. In terms of sensing, we use a lot of electrochemical sensing and optical sensing. I will show a few examples on that. But also, we're interested mostly in how we can convert CO2, which is, all the problems related to CO2 nowadays, to added value chemicals through photo or electro or the combination of the two. And finally, indeed, it's the energy storage using particularly metal oxide and carbon-based material. Well, back to graphene. I think you have learned a lot on carbon nanotubes, but also you do know a lot on graphene, because it has been now for quite a while around. Even it's a new material, but it's still more than 10 years where people are really actively involved in this field. And as I told you before, the important thing, and what makes, I think, the advances in this field very fast, because there was a lot of knowledge generated on carbon nanotubes, and most of the time, indeed, you find relatively the same. Actually, processes, functionalization, and even application, they were just transferred from carbon nanotubes to the graphene. And that's indeed, then you can really go fast in terms of applications and also gaining knowledge on this material. Fortunately, you have seen probably now it starts a bit, I would say, to slow down, but probably 4 or 5 years ago, you almost see hundreds of papers every week just on graphene. And the reason, indeed, because there are so many applications where graphene really can find or can add, actually, or bring something, additional functionalities that you cannot really perform or achieve using different materials. So certainly there, I guess, depends on the community coming from. If you're coming from physics most of the time, or electronics, you're interested by CVD, pure graphene material. That's exactly what you call graphene. However, for chemists like I am, we're more interested in what you call chemically derived graphene, because it's cheap, easy to produce, and also you can produce at a larger scale, so it becomes cheaper and cost effective. And that's exactly what you call the Hummers methods. And this starts from graphite, which is coming from, it's a natural material, and you just oxidize, and you lose all the properties of graphene when you oxidize graphene oxide. It's really an insulating material, it's not conducting. It becomes completely different from what you call really graphene. So you have to remove all these oxygen functionalities to recover the graphene type material. But of course, that's not always as simple, but also there's always a confusion in naming. People will call whatever graphene, although, I mean, as soon as you exceed a certain number of layers, a few layers, then you lose the properties of real pristine graphene, like CVD graphene. Then you should not anymore consider that as graphene or reduced graphene, but it's graphite-like material. But, well, no matter what that, it's exactly what I said now. So you see, this is just breaking up the graphite sheets from graphite oxide through oxidation. So you make something which is negatively charged. So you can easily disperse that in water. However, you lose all the properties of the graphene. Then you have to reduce and remove this graphene, this carbon oxygen containing groups. The problem is, if you remove all the oxygen containing groups, then you are coming back to the initial material, which is graphite, because you have the stacking. It's exactly what is graphite. So you have to be careful that you don't remove completely, or you have actually to stabilize the material that you don't recover or go back to the graphite. Otherwise, you're just, going both ways, but you're losing your time and energy and money, of course, without making the real material. What I said, it's indeed, you see, graphene oxide, it's very nicely dispersed in water. You can disperse it, and the dispersion is stable for months without any precipitation. And if you make a thin film out of it, of this graphene oxide, you see it's hydrophilic. This contrasts with the reduced graphene oxide, which actually precipitates out of water, and you see it becomes black. It means because you have this aromatic structure and this conjugated structure. However, you can process easily this in different organic solvents. So we can actually disperse it in THF or many other polar solvents. And if you're not happy enough, of course, there's a lot of this. Is actually a collaboration we had with a young PhD student who came in from India for 6 months in the lab. It's to go a little bit further to improve the properties of the graphene or reduce graphene oxide through doping, or making porous material out of the graphene so they can increase the surface area. Or you can even make what you call graphene quantum dots. It's just very small structures made out of graphene. Now, whether you buy the graphene or graphene oxide, whether you make it, you have to transfer that, because otherwise, if you're with a CVD graphene, it's mostly grown on copper or nickel, but for a lot of application, you want actually to have it on different substrate. And in particular, I would give you examples where we want to use it for optical sensing. So we have to transfer that for SPR, so it's a surface plasmon resonance. We have to transfer that on gold sample. But also you can, if you actually deal with the material you buy or you make, which is called chemically derived graphene, then also you want to transfer. You can have just a droplet because you can have it in a solvent or in water if it's water dispersible. But there you don't control the number of layers. So you let the water evaporate, and then you have the restacking of the graphene sheets, and that potentially can lead to actually lose the characteristics of the graphene, okay? So you have to find really different ways of transferring that. I will cover mostly the Scotch tape and the electrophoretic deposition. Inkjet, I think you have seen everywhere, because here you're not limited by the number of layers. You don't care because you mostly make a very thick film, so that's not an issue. But I would really mostly focus on the techniques where you can control the number of the layers you transfer to another substrate. The first one, as I told you, I will tell you why we want to use gold and why we're interested actually in gold modification with graphene. So the first technique, I think that's exactly how the Nobel Prize was awarded. It's the Scotch tape. Typically, you buy your graphene on nickel or copper. You apply Scotch tape made out of polymer. You press against the nickel graphene, and then you have a transfer of graphene to the Scotch. You just it to release. It's like a stamp. Then I take this this graphene transferred on the tape, and I can actually print it on different materials. It could be glass, it could be any substrate. So this is a very nice technique because you control really the number of layers. You can even transfer a single layer graphene to any substrate. However, then you have to release this Scotch tape. Otherwise, you end up with the substrate, graphene, and Scotch tape. Of course, you can do nothing with the Scotch tape. It's a polymer material. It's very thick. So you have to remove that. You can anneal it to 120 degrees C. But often, this leaves actually a lot of impurities on the surface. And to remove all these carbon-based impurities, you have to anneal to 500 degrees C. Therefore, this process we experienced several times. It's always not reproducible. So it's very tough and doesn't give actually good results. And when you make devices, you need really something process which is very reproducible. So we moved to another technique, mostly used in techno, because you see, you come back, you have the PMMA, which is just a photoresist. The same, you start with graphene on copper. So what you do, you deposit a thick layer of PMMA, a few micron thing, that's not a problem. And you etch the first layer of graphene here, which is on the back of copper. You end up with copper. Again, you etch the copper. It's very easy. You just in this mixture of oxidant. You end up with a freestanding graphene, 1 or 2 layers here on PMMA. Then you can transfer exactly the same way to any substrate, with the advantage this time because PMMA can be very easily removed just through acetone washing. And this actually works very nicely. We had a very high success rate and very reproducible. So the first application of this we wanted is on making actually sensitive devices for optical sensing. SPR, it's surface plasmon resonance. Typically you use this, it's probably in the 80s, I think it was in this short, we can buy it of course since 80s or late 80s. And very much used in biology because this technique is very nice. You can study biological interactions, so you can have access to the affinity constants, and you can also follow in real time the interaction between biomolecules. The way it works, it's very simple. You have a laser here, it's a general red laser, 670 nanometers. And you have here a glass slide with a very thin gold film. Well, of course, you have the adhesion layer of titanium in between, which is 5 nanometers, below 5 nanometers. And the gold layer is about 45 nanometers. And what's happening actually when you choose, normally light is reflected from the middle, but at this interface, if you are to the right angle, you have what you call a minimum reflection. And this minimum of reflections will keep the same angle. Now, if I change the refractive index on the gold layer, it means I can put biomolecules on it, or chemical, or polymers, whatever you want. You change the refractive index, you change the mass, and this actually minimum shifts. And when it shifts, that's exactly the amount of material you have on the surface. So you can detect the change of refractive index mostly, but which is indirectly connected to the mass change on the surface. While often normally what you have, actually you have to functionalize the sensor to make it selective and sensitive. So typically you buy these slides, so they have a thin polymer film with cyclodextrins, or you put what you call this alkanthiol functionalization layer on the gold surface. So the reason why we wanted to replace these functionalization layers with just a single or 2 layers graphene, there was a paper that came out in 2010, just a theory saying, well, if you have a graphene layer on the gold surface, you should be able to improve significantly the sensitivity. So first we wanted to indeed to check that, but also because graphene has a high surface area indeed and has really very different ways of functionalizing. So it offers really much more opportunities for making different sensors. So we had CVD graphene. You can see it here with the Raman spectrum here. You have very nice graphenic lines. This is the 2D related to the number of layers. And you see very small D line, which is called defect or defect-related Raman band. And now when we transfer that to gold, you see the D line increases slightly because you don't have you actually transfer from copper or nickel to gold. This mismatch is not the same. So indeed, you generate more defects on the graphene layer. However, if you look from the XPX spectrum on the carbon, it's really clean. Before and after transfer, there is no impurity, as I said before, when you use this Scotch tape. Now, we took the simplest example. We have the gold SPR and the gold modified with graphene. And on this, you just add proteins and you follow the signal over time. You just do kinetics. And what you see Here you have just, if you ignore, you have a certain response. However, if I use exactly the same amount and I use the SPR modified chip, I double almost the signal. It means you gain almost to the sensitivity just by adding a very simple 1 or 2 graphene layers on top of that. Here I will just give examples on how we can use this. We use it for DNA hybridization. It's simple because a single DNA will absorb very nicely in graphene. Without anything, you just put it, it absorbs because you have this pi pack stacking, hydrophobic interaction. However, if I bring now the complementary DNA strand, it will hybridize with the DNA strand on the surface, and this hybridization will break the interactions of DNA with the graphene surface, which are more stronger. You know, the hybridization has energy input which is much higher than the interaction of the simple graphene sheet with the DNA, and this goes off the surface. So we can really very nicely do that. And if you do non-complementary, of course, it's not the same way. It doesn't work the same. So we use this concept, and we could detect DNA with hybridization with a very nice sensitivity below to 5 femtomolar. And of course, we extended all different functionalization schemes and different actually applications to sense either bacteria, but also to study bacteria, sugar or lectin interactions, and also different types of biomarkers detection using this technique. Now, whatever I actually covered, it was mostly on CVD graphene, but as I told you, with chemists, we really prefer working with something which is cheap and easy and available. It's this chemically derived graphene. The same, what people mostly do, you take a single drop of this or a few drops of this to any substrate, but you end up actually with a relatively thick layer. So you most of the time you lose really the graphene, I would say, characteristic and properties. So what we wanted to do to check if we can use what we call the electrophoretic deposition, and this is a process applied in industry, and it works very nicely on a large scale. You can use it in square meters, depending, of course, on the instrument you have. And the concept, it's so simple. You have 2 electrodes, you apply your potential. In the electrolyte or the medium, you have something which is charged. Graphene oxide is negatively charged, but you can make it positively charged if you mix it with metal ions, for instance. And then what's happening, these actually what you call colloids or molecules or materials in this medium, if they are positively charged, they go to the negatively charged electrode. The opposite way, if they are positively charged, or if they are negatively charged, they will actually migrate to the positively charged electrode. So we can really very easily and simple and quickly modify any electrode material. However, the difference between the former one, here I have to work with conducting electrode, because I have to apply a voltage. Otherwise, I cannot do it on glass or other types compared to the transfer of CVD graphene. Okay, so this is just graphene. You can see it takes about 20 seconds. I can transfer about 5 to 6 reduced, and I can transfer and reduce at the same time the graphene oxide. And I can limit really to 5 to 6 sheets, not more than that. Well, if you look at the XPS, of course, it tells you that the graphene, when it's transferred, it's also reduced at the same time, but you have defects a lot because chemically derived graphene is full of defects at the edges. Interesting enough is that if I mix this graphene oxide with nickel or nickel with a biomolecule or with any metal ion, I can actually make hybrid materials very easily in one step in less than a minute. One example is I took graphene oxide with copper salt. You just apply a voltage about 50 volt, 1 to 3 minutes. I can actually control the thickness, and you end up with nanoparticles of copper oxide. You can see here completely actually in a network with graphene. You can see in between the particles very easily, very simple. And this we apply this for actually for glucose sensing or glucose oxidation. Even in plasma, you can detect without any enzyme with quite a good detection limit. The important actually part of this technique, because I apply a voltage, it means the migration happens in an electric field. So I can really come and selectively modify a very small electrode, which is about 10 micron in a microsystem. The whole microsystem here is about 6 millimeter by 1.4 centimeter or 14 millimeter. And you see I have different electrodes. I have gold, platinum, and silver, the counter, reference, and working. And now if I want just to modify this, if I use a drop casting, it doesn't work because the drop will completely actually wet the whole surface and will modify the silver and the platinum. If I want just to modify the gold by applying the electrical field, you will see this electrophoretic deposition will allow me to just selectively only functionalize the gold electrode. And you can see it here. Now we just record Raman spectra after graphene transfer. If I take, this is the gold, which is about 10 micron in size. Here in one, you see it's a flat line. It means the graphene is not transferred outside the gold. However, if we take it on the gold surface, you see that the spots 2 and 3, here you see the characteristic bands of G and the D band. It means I can really functionalize a very small microelectrode in a microsystem. And of course, you can see it really responds nicely. You have an increase in the current as compared to non-modified electrode. So we use the system for dopamine detection. I will tell you exactly why we want to use or detect dopamine. Of course, it's a neurotransmitter, but also in a lot of countries, actually, people do give dopamine for animals to build muscles, but that's really problematic. So, excuse me. Then to confirm that the sensor is really performing nicely, so we compare the dopamine sensing using our microsystem and also another technique which is called high performance liquid chromatography, and you see we get exactly the same dopamine level in chicken meat or beef meat comparing to the systems. It means we can really divide or design a very small microsystem for using it for dopamine sensing in meat samples. Other type also we can use a polymer. We can transfer or make a composite material of a polymer. This is polyethylene and graphene oxide, and we can transfer that very easily to any surface which is conducting. And what we did with that, then we just modify it with an antibody which is actually directed towards a bacteria. It's a uropathogenic bacteria we can often find actually it's responsible for urinary infections. And you can see if I don't functionalize the polymer with the antibody, there are no bacteria on the surface. However, when I functionalize that, I capture all the bacteria in the sample. So we can really have a very selective and sensitive capture and detection of bacteria using electrochemical method. And they can actually reach down to 10 bacteria per ml, which is quite really very sensitive. Well, there's some examples you can even probably to one or a few, but it's still very sensitive given the way the sensor was made. Okay, yeah, this is just, you will see afterwards. I will, how many minutes I have, or it's okay? I have about 10 minutes?
Yes, 10 more minutes, sir.
10 more minutes is perfect, it's fine, it's enough. The second part, and now I think I will focus mostly how we can use graphene films in biomedical application. I guess when you look at the image on the left side, you know, people with diabetes, when they are treated, they have to inject insulin on a daily basis just before they eat to actually regulate the glucose level in the blood, otherwise. Okay, so this is actually quite painful, and also injecting insulin every day on a social basis is quite difficult and also handle, because most of the time you have to isolate yourself in a way that people don't look at you, they don't see you. Another problem related to this, indeed, it's painful, but also you can contaminate easily your skin because your infection over and over, you can have bacterial infection. So what we thought, and very naively, if we can really have a device that we can actually deliver this insulin through the skin, okay? That would be ideal, because then we can have a patch and we can control the patch through a stimulation using light or using hearing. Indeed, it's a thermal delivery. It's a photothermal delivery. It means we can control the delivery through actually applying a photothermal. I'm hearing some noise. I don't know if it's an echo or just somebody is talking.
Wait, Rabah, there is something.
Okay. Okay, this is better. Thank you. So I guess for people smoking, you all guys know what is nicotine patch. So the way it works, indeed, if one day you want to quit smoking, what you do, well, of course, you have to be willing, otherwise it's very difficult. You do some exercise. But also, there are patches you can buy, and they have this nicotine. So what you do, you apply that against your skin, and the nicotine will actually diffuse through the skin. You get enough nicotine in your blood. It's like you smoke. Then over time, you just reduce the amount of nicotine until you don't have this dependence, because you don't need it anymore. So this works very nicely. Of course, you go to any pharmacy, you can get this patch. However, if you look, the nicotine is very small, it's lipophilic, it means it's not water soluble, and also it has a very low molecular weight, it's below 500 Dalton. Now the idea, if you want to use the same patch that would have been ideal for delivering drugs, any drug that would be perfect because you don't have to inject, you don't have to do intravenous, you don't have to, but that doesn't work because the passive release doesn't go. Any drug which is higher than this or different structure will not go through the skin, which is also fortunate because our skin is meant to actually protect us from the environment. Otherwise, anything that is in the environment will diffuse through the skin and will just probably, except if we have an immune system which is like Superman, otherwise we die immediately or over time not even live for a longer time. So the reason why actually this works, we're protected from the environment because our skin has what you call this outside, it's about 15 micron actually thick layer, which is called stratum corneum. And it's a fat mostly, so that prevents actually molecule to go through. They stack just on top. The reason why nicotine can go through because it's lipophilic, so it's a fat, it's soluble and can diffuse, it's small as well. But if we want to do something else, it would not. And I told you we wanted to really naively, if we can use that to deliver insulin through the skin. Which insulin, if you look at the molecular weight, is 5,000, almost 6,000, and why nicotine is about 500 Dalton. There are many techniques you can buy and actually equipments you can buy today to go through or to actually overcome this stratum corneum barrier. So through applying either high current or voltage, but also I think the most important one, you can use thermal ablation, but it burns, actually creates macro channels, but it can also over time with a laser can burn the skin. I would say the most really interesting technology is these macroneedles. Why these macroneedles is really interesting? Because the macroneedles, they will go and just actually punch through this stratum corneum. Then they can deliver directly under the stratum corneum, and then they can diffuse slowly to the blood. This works very nicely. However, the problem, most of the needles, and you use polymer needles, they will dissolve up, and actually you punch, you put them against your skin, they will dissolve, then you have a burst, and then you have to continuously provide a new sample or new macroneedles, and that's forcingly it's costly, but also you don't control the release because it's a burst. It means if they want to know exactly the amount, and they can control the amount of the drug or the insulin they want to release and deliver. So that's what I said. So the idea for us was that can we use the photothermal driven delivery? Why? It means if I apply heat, I should be able to open channels, but only spontaneously. They will close up when I stop the heat. And then when you open the channels, then the drug can deliver, can actually through and permeate through this stratum corneum. The advantage of this technique, it's a patch. It means I can actually, even over time, the idea was also to have a sensor that can detect the level of glucose, and then I can adjust how much of insulin I can deliver. I can control it because only request it's a photothermal, just light emitting diodes. And with time, I can really switch on and off and control normally the insulin delivery through. Well, and we wanted to use what you call the photothermal, but in the near infrared. The reason why, because in the near infrared here, there's a very small window, about 980 nanometers, where nothing absorbs. Not the skin composing the proteins composing the molecule, the skin, nor water. It means I cannot generate any damage for the skin. And for that, graphene is ideal, because graphene, it's black matter. If you have several layers, it absorbs all over from the UV to the near infrared. It has a high surface area, so we can really load a huge amount of molecules. And also, it creates it efficiently, have a high conversion efficiency of photons to heat. So to do that, it's a collaboration with a colleague from Turkey. We made just a material, a composite material of polymer with graphene. So it's very easy way of doing it. You just polymerize this dimethyl acrylate with graphene, UV, and you see on the left side when you don't have graphene on it, you have very transparent composite thick film. When you have graphene, you have something which is completely dark and black because of the presence of graphene. It absorbs light. Interesting enough, you saw it's a porous material. So if it's a porous, it's a hydrogel, so it can really load a huge amount. It can also protect it because it's an environment which you have a lot of water, absorbs everywhere, thermally stable because I have to actually generate heat. And importantly, if I expose that to light irradiation at 0.7 watts square centimeter with just a laser at 980, you see you can heat up over 60 degrees. I don't, of course, need this high level of temperature, just about 50 should be more than enough. All said that, we optimized indeed the ratio between the polymer and the reduced graphene oxide, the pH at which you load. I will go fast now anyway. So what's important now, but imagine that you have a molecule inside this hydrogel, but you cannot release it. That's problematic, because if you cannot release it, it means it's stuck in the hydrogel, you cannot make use of it. That's fortunately not the case. I can easily, when I expose this to the light, release the insulin. I can again load it and release. I can reuse it. It means I can use that over days and days. It means it's something I can really store insulin and I can release it when I want. It means when just I turn on the light. Another point which is really critical, imagine now that the insulin, because insulin has an activity, that when it's loaded and released, it doesn't have any more activity. You lose the activity. Then, of course, you can do nothing with this. Again, we're fortunate when you look at the native insulin and the photoreleased insulin has even much higher activity. The reason why, we don't really know why, but it's definitely reproducible. It's not 10, it's not 20, it's more than that. Okay, the next, I will just go 2-3 more slides, and then I think it's the end of my talk. This patch we made, or this hydrogel, it's really compatible. It's very biocompatible. You see, you don't kill cells if you grow the cells on top of them. And now, to be sure that we can apply that for delivering through the skin, you have to use a skin. You cannot use human skin. It's just illegal to use it. So you use what you call the pig ear skin. It resembles a lot the human skin, with the advantage, of course, it's cheap and free. You just go to the slaughter, you can get as many as you want of the pig ears. And you can see here very nicely the stratum corneum. It's a very thin layer. So what you do, the way you do it, then you take this pig, you apply the patch on top, and you irradiate, and you look if there's anything that can diffuse through. Then you get it here in the small vial, and you can analyze indeed whether the insulin can. And we see very nicely, very nice pharmacokinetics. You have slow insulin diffusing through the skin, but it's very slow. You cannot really make use out of it for real application. But this is science, of course, and it takes time really to optimize that. So we went a little bit further, and we looked, you make this insulin fluorescent, and you see whether it's really diffusing. Indeed, you can see it diffuses completely through the skin. So it works. You're happy, but of course, it doesn't work to the point you can really reach a product and right away apply it for diabetes treatment. But it's very good and encouraging results. And most importantly, this actually patch, you can use it for other things, for wound healing, You can see it here, but also for delivering other type of molecules which were not possible to do before, such as cRNA, but it could be any type of molecules. I think I came to the end. I just want to end with the acknowledgement of different actually funding agencies, because this is really important. Otherwise, we cannot really do the research the way we want and can advance exactly the way we could So thank you for your attention, and I would be really happy to take any questions if you have any.
Thank you, Dr. Rabah. I have few questions.
Yeah.
How to stabilize a single graphene layer?
To stabilize a single graphene layer, well, if it's on the surface because you grow it, that's not a problem. So when you buy the graphene, if it's CVD graphene, it's grown on nickel or copper. On nickel or copper, you have roughly 1 to 2 layers. So that's not an issue. The problem is the graphene you make out of the chemistry. It means you reduce graphene oxide in solution. You have to stabilize that. And the way you only can stabilize that, you have to add polymers or some molecules. They can actually keep a charge or provide a charge which is positive enough or negative enough that you have a repulsion between the graphene sheets. That's very problematic indeed. And often, that's, I said exactly initially, what's happening if you don't do that. Because of this pi stacking, you go back to the graphite type. So you will have over 10 or 20 layers. Then, of course, it's not graphene anymore. It doesn't resemble graphene. It resembles more graphite. So you can stabilize a single layer of graphene in solution using polymers or different types of molecules. It's possible.
Okay. Second question. Can we prepare graphene using chemical vapor deposition method?
CVD, yes, but then you have to be equipped. But yes, so there are a lot of and many laboratories growing graphene, the CVD graphene, yes, but you can buy it as well. The same for chemically derived graphene. For CVD, I think that's not an issue if you're equipped. But the problem is mostly for chemically derived graphene because it's not a reproducible process. And because the way you oxidize it and the way you reduce it will affect a lot of the properties of the material, the end material. But CVD is no problem. Yes, it's very nicely controlled. It's a very known process, and there are very specialized laboratories for that.
Okay. Next question. What is the adsorption efficiency of reduced graphene oxide?
Yeah. Adsorption efficiency, again, it will depend. It's a surface process. It means it depends on how the graphene is modified, what type of functional groups you have on the surface, what type of molecules you are trying to adsorb some graphene. For instance, the most strong adsorption process is when you have aromatic molecules, because you have these pi-pack stacking interactions that will favor strong interactions between the molecule and graphene. However, you can have also hydrophobic type or hydrogen type, because on graphene, even it's reduced. I'm not talking about pristine graphene or CVD graphene. I'm talking about really this chemically derived graphene, what you call reduced graphene oxide. You have always oxygen containing groups. And that's indeed, you can have hydrogen bonding. But definitely what dominates the absorption of a molecule from the solution onto the graphene surface, it's the pi-pack stacking interaction. It's the aromatic interaction. So if you have any aromatic interaction, amino acids or polyaromatic, that's exactly, it will stack very quickly and very strongly. You cannot even get it out. That's exactly why people use what is pyrene type molecules to functionalize graphene, because it forms actually very strong interactions with the graphene layer.
Okay. Which substrate gives more compatibility for the applications you mentioned?
Yes, there are, I think probably Stefano also have seen this. I think, you know, there was at some point, there are quite a lot of papers actually on the, whether graphene is antimicrobial or it's antibacterial or not. And indeed, it turned out, no, graphene actually, if it's very nicely sitting horizontally on the substrate, it's biocompatible. However, what's happening often, if you have graphene, sometimes because of these hydrophobic interactions, you have the tendency to have this standing perpendicular to the surface. When it stands perpendicular to the surface, then it acts like a knife. And if you put a cell or a bacteria, anyways, no matter what type of cell you put, then the graphene goes in between, it goes into the membrane and it can open up channels, and then you empty the content of the cell and you kill the cell. So then people call that antibacterial, but in reality it's not antibacterial, it's just a mechanical effect. So if you have a flat graphene, it's biocompatible. But if it stands slightly like a knife, then it could be potentially open up, interact with the membrane and open up the membrane and can kill. So graphene itself is biocompatible, yes.
Okay. The last question, what is the difference using graphene-coated PSR and non-graphene-coated PSR in DNA hybridization?
Okay, the main difference actually, well, the presentation is not there, it doesn't matter. If you use non-coated gold chip for surface plasmon resonance, you have to modify the chip with a thiolated DNA. So you have actually to have a monolayer of thiolated DNA, and then you do hybridization of that. However, on graphene, the concept is completely different. The single DNA strand is just absorbed on graphene through this pi-pack stacking interaction. And when you do the hybridization with the complementary DNA, this actually is released from the surface. So in a way, you measure negative signal, you lose signal, while in a normal SPR, actually you measure a signal that is added on the surface. While we have graphene, you measure a signal which is out, which you lose because you lose the material, so in a way, it's a negative signal. So, and it's completely different because I don't have to modify the single strand DNA, it's just an absorption. While on gold, I have to modify it with a thiol or with an NH2 to have a covalent bonding on the surface. This is one thing. So it means, again, in terms of DNA functionalization, purification, I just take the DNA as it comes, separate it from blood or from serum. So I don't have to modify the DNA, and I can reach much higher actually sensitivity compared to the normal gold SPR.
So thank you, Dr. Rabah. There are a few more questions. I have given your mail ID to the participants so that they will directly contact you for further queries.
Great.
So it's really an informative session, Dr. Rabah. I once again thank you. I also wish to thank Dr. Stefano, today's speaker, Dr. Mohod Bahanina, webinar chair, Father Justin Prabhu SJ, Samson sir, and Sudhagar sir, Office of Media Relations, Loyola College, for today's session. There are few announcements for the participants. Tomorrow we will start the session at sharp 3 p.m. Indian time. A new YouTube link will be sent to your mail for tomorrow's session by today evening. Kindly use the new link to join for tomorrow's session. Regarding the feedback form, tomorrow 25th June from 5 p.m. to 9 p.m. Indian time, the feedback link will be enabled and you can fill it for both the days together. Please don't open the link today. It is disabled now. You can open it tomorrow from 5 p.m. to 9 p.m. Indian time. And regarding the e-certificate, we will send the link to your mail from tomorrow night onwards. Please fill up the details correctly. It will ask your name, college name, and other details, because the link will automatically create your certificate. If you wrongly type in the certificate, the link, then again we cannot give you the correct certificate. So while opening the link, please fill up the details correctly. You will receive your link and certificate before 30th June 2020. Kindly be patient, and if still you have any problem, you can mail me. I hope there is no more questions. So thank you one and all. See you tomorrow at 3 p.m. Indian time again. Thank you.
Okay, bye-bye.
Bye-bye.